Good afternoon. Thank you for being here. Thank you for being in this presentation. Thank you for the GPD team for putting this great event together for so many years. It's a great way to come to Finland, which is a beautiful place. Come from Mexico, Houston, Texas. My name is Javier Sanchez-Gil. I've been with Crystal Curva for over 26 years, and the company has been curving glass much longer than that. Today, I would like to talk to you about how we take the fabrication of curved glass to its limits and meet most of the architectural requirements, which are constantly evolving and pushing the envelope. Over the last few years, there has been a lot of changes in architecture, and I'm going to show you a few pictures of projects that we've done where you can see different curved glass applications. You can see a lot of changes happening. For instance, this is an undulating wall with curved reflective glass, something that I could not have imagined a few years ago. You can also see in these examples that curved glass takes a key feature element in many design. It's like a central stage. Like in this case, it's a simple design and also shows new technologies applies to curved glass, like a giraffe printed on the glass. Again, new things happening both in flat glass and curved glass. Another example where you can see how curved glass makes a simple feature in a building a key feature, a simple staircase, and is enhanced by the curved glass. Or a nice undulating wall in a hospital. This is a great example of changes in technology. It's a structural wall made out of curved glass and supported by glass fins. Again, something that you could not have imagined not too long ago when I first started. So as we can see, architecture continues to evolve. Architects are at work. How many architects are we here? Quite a few, huh? So you guys are working hard, putting a lot of creativity into your designs and pushing the envelope. And that's what we like. We like those challenges, and that's what I want to talk about. Curved glass, it's a very important or an interesting feature in many designs. It's not a volume-oriented feature, but it's something that gives something to talk about. Energy and safety codes have continued to evolve. They're not getting easier, they're actually getting tighter. And glass technologies have also been evolving a lot over the last few years. New coatings, new interlayers, new processes. So all of these advances have taken the manufacture of fabrication of curved glass to greater levels of complexity. Think about this, when we're curving glass, we're actually deforming it. So if we have a coating or a fret on, it's got to stay on. Or if we're trying to put two pieces of glass together with an interlayer in between or a spacer, that challenge becomes higher. So how do we cope with these stringencies and these situations and still be able to fabricate a lot of solutions for the ever-changing architecture? Because we can make a lot of things with curved glass, infinite possibilities. Well, I like to say three things about this. The first thing is that there has to be know-how and experience, and that's a lot of trial and error, and that's a lot of years of experience. There has to be some, and good fabrication technologies are very important, and something that is, I want to say, not new because it's always been around, but I want to make it a focus of my presentation. It's close collaboration between the design, the building, and the fabrication team. But close collaboration, I don't mean just talking and having nice coffee and doing emails together, but getting deep into having a common objective and working through the solutions to find the best possibilities that will accomplish the goal of the project. So main goals of collaboration are going to be to research materials that meet the design and performance requirements. And if there has to be a compromise, if there has to be something that somebody has to give up, be open about it and work through it to accomplish a project goal. To illustrate what I'm saying here, I would like to talk to you about 2 case studies where collaboration was very important to accomplish and to be successful at the end of the project. The first one is a corporate headquarters in Detroit. We were first approached by the architectural team way before the project started. And the architects wanted to create a facade where they had diamonds on the facade. So you can see the rhomboid shape on this picture. That's a diamond. And that's the shape of the glass. So the architects wanted to accomplish this, but they also had to take into consideration certain important requirements. The first thing is that the weather in Detroit is harsh. It's cold in the winter, very cold actually, and warm in the summer. So the thermal and solar performance of the glass was very important. The second one was that so they wanted diamonds. They wanted the brilliance of the diamond, the clarity of the diamond. So they wanted to also have a very clean facade, so no metal support. So the structural performance of the glass was very important. And obviously, the aesthetics were necessary because they wanted diamonds. So clarity and a neutral color was also a need, a must in this facade. So they had this idea of the diamonds, and this was the shape of the glass to begin with. It had a radius of 200 millimeters and 2 flat parts. And 200 millimeters, it's a very tight radius for a coating. If we go by the book, coatings won't take less than 1,500 millimeters. This is almost 8 times less than that. So what did we have to do? Well, we had to work with them in close collaboration and try to find solutions to this situation. And we did a lot of research, a lot of tests for a few months, 6 months, and we did not find that any coating could take the curvature of the glass. Coatings would crack under the pressure of the curve. So we had to find coatings that wouldn't do that, and no coating did that. So what did we do? So we went back to the design team and the glazier team, and we came up with a solution which was to increase the radius from 200 millimeters to 400 millimeters, which is twice as much the radius, but the shape of the glass did not change much. It was only 11 millimeters of depth difference. So the shape of the glass really stayed the same, and the coating could also stay there. So the coatings that we came up with, and we were successful at keeping the design intent, and by changing the radius, the design intent stayed the same, but the radius was changed, and we were able to accomplish also the thermal and the performance aesthetics that they needed using the following products. The first one was we use an XIR interlayer, and we also use a hard coated low E product and as the internal piece of glass. And for the structural performance, we used a DG41 and 2 layers of 10 millimeters glass. And this is how the glass looked like in the end. With a 400 millimeter radius, 2 layers of 10 millimeters glass, and the DG41 and XIR interlayers. That's the shape of the glass. It's about 2 meters by 4.2 meters in height. And so that's a triangle shape like you can see in the screen behind me. So the next step, also in collaboration, was to build up actual samples, real size samples, what we call mock-ups. And we put them together for the owners and the design team and the building team to come down to our facility and inspect them. They needed to check for clarity and brilliance, and they needed to have the neutral color that they wanted out of these diamonds in the facade. And they had very stringent optical requirements. And they were very pleased with what they saw. As you can see in this picture, the glass looked very nice and very clean. And so we moved on to the next step, which was actually how are we going to go about the installation of the glass now. So again, in close collaboration with the, in this case, with the glazier, with the glazing contractor, we determined that the best way to approach this, well, first I got to rewind a little bit. The glass had to be annealed because of the shape, so there was no way that we could drill the glass to a facade. So So engineers determined that the glass had to be glazed with a 4-inch or 130 millimeters depth silicone bite. And so that's a very special silicone bite. And so we determined that the best way to do that was to glaze the glass in our facility. And the customer would send, the glazier would send the metal already bent. We would put it together in a facility and put the special silicone bite onto the units. So this way, this also helped in the efforts of installing the glass much faster, because the customer would just take the units and just hang them in the facade. And this also was a great way to accomplish that. How many times have you heard that the metal and the curved glass don't fit together because the curvatures are different? So in this case, we had the metal, we have the glass, we had to put them together, and if they don't fit, they don't work, we didn't ship them out. So that was a great way to put them all together and ease up the installation process. Again, collaboration. In terms of collaboration, well, this is the special team that we put together to glaze the facade. Again, it was a special silicone depth, so we had to put a special team together to do this. Another example of collaboration in this case was the inspection method. Every piece of glass had to be fully inspected, 100% inspection. And the architects and the building team participated 100% in the inspection. And that was a great help too, because by doing this, by allowing to work together, we were able to ship the glass, and once it was shipped, it was good, so it was easily installed, quickly installed, and so that was a great thing also. Another example of good collaboration. So this project is a good example of team collaboration between the design, the building, and the fabrication team. And we accomplished here, through collaboration, aesthetics, the quality required, and the thermal and structural performance required. We're very proud of this project and the team that we put together. The second project that I would like to talk to you about, it's another good example of good collaboration. And there were different situations in this particular project that I'd like to talk to you about. This is a project designed by Foster out of the UK. It's in Iowa City. It's an oval-shaped building. It's like a football. It's actually across the street from a football stadium. And in this case, the architects had, and the hospital actually had very specific requirements. Well, first, Iowa, for those who are not familiar with the US, Iowa is located in the Midwest, and it's a place where there's big tornadoes, and these tornadoes are much stronger than hurricanes. And they're not as massive in terms of size, but they're very focused, and the winds are really, really strong. So the hospital wanted to have a building that was a tornado resistant building, and it was a shelter. And so the glass had to have very specific structural performance qualities. The Iowa weather is also very harsh. It's very cold in the winter, warm in the summer. So thermal performance of the glass was also very important. And the hospital wanted the patients to feel good. So they wanted to have big windows, as big as they could, which goes against tornado resistance, right? Because the bigger the window, the thicker the glass is going to have to be. So that was an interesting point there. And they also had tight deadlines in the project, and so quality and consistency of the production was very important. So how did we collaborate? In this particular case, collaboration was focused first with the owners of the building, the hospital, and especially with the manufacturer of the interlayer. We worked together, we put a lot of different makeups, and we tested for tornado resistance, which again, it's very strong winds, and so the glass has to be very strong, and even stronger when you're taking into consideration that they wanted large windows. So that was a very interesting challenge. We had to put together many different makeups and test in a lab with the assistance, again, the collaboration of the interlayer manufacturer. Once we did that, we were able to come up with a makeup that would meet the performance. And as you can see, it's a pretty massive makeup. There's a huge interlayer. It's 6.1 millimeters. And the silicone bite of the units were 50 millimeters. That's 2 inches. That's more than twice what a regular IG line can put together, can inject. So that was another example of how we had to collaborate with the, in this case, with the machine manufacturer to make sure that we could inject that amount of silicone. We gathered the teams together again, the hospital and the architects and the building team came down to our facility and to inspect the glass, the quality of the glass, the aesthetics of the glass, to make sure that they were actually accomplishing what they wanted, their vision. And so that was another very good exercise where the team gets together and get to know each other very well and work through the bugs of the process and make sure that the project is going to be successful. And here you can see some examples of that inspection at our facility. This is a picture of the project. This is the tip of the building where the curved glass is installed. This is another view of the building. You can see the tip and also the flat windows on the side. The 12th floor, the upper floor, it's a neat feature of this building. It's above the level of the stadium, so they take the kids to the 12th floor and they get to watch the game live. And halftime, the players wave back at the kids, so they play that on TV. I thought that was a very neat feature of the building. So anyway, the bottom floors have also a nice undulating facade, a nice curved glass wall. So again, this is a good example of team collaboration to accomplish something good, a nice project, where the design and the building and the fabrication team get together and we are able to accomplish the aesthetics needed, the structural performance, the quality required, the thermal performance, and a large volume project with a tight schedule. So to conclude my presentation, I'd like to say that every project is unique. And projects are even more unique when there's curved glass involved because curved glass has 3 dimensions to it. So it's very, they're all going to be different. It's also important to mention that curved glass is not a simple product to manufacture, but there are infinite possibilities with it. And the key to accomplish those possibilities are obviously the know-how and the experience of the fabricator, the technology, and especially teamwork and deep collaboration. Thank you very much.
So many thanks, Javier. Are there any questions from the audience?
Hi, I'm Jürgen Neugebauer from University in Graz in Austria. I have one question to the project in Michigan with these triangles. How you performance the gaps between these elements? Is this simply silicone or is it free? It's open?
Yeah, the joints of the glass were butt glazed. That's how we call it in the States. Butt glazed, basically they come together about, I want to say 12 millimeters, 9 millimeters, I really don't know how much. And there's a silicone joint, yes.
Hi, I just want to know if the view from the inside, if you're moving along the facade, I have the conception that I would get car sick. Do you have any comments to that?
You mean in the first project?
Yeah, in Detroit.
I do have pictures showing that condition. And no, you don't get car sick like you're saying. Actually, Paul, you're here. Paul, he's part of the glazing team, and he can probably witness to that. But no, the optical qualities of the glass are pretty good, and the views outside are very nice.
Okay.
That was a big item for the owner of the building, and they did inspections of multiple manufacturers across the world. And the optics was a very important item for the owner, and it was remarkable actually. In the end, if you stand where the curves are, it's pretty imperceptible. Everybody was very pleased.
Thank you, Paul.
I have a question about the Detroit project. You said that it was made on annealed glass, yeah?
Correct.
Yeah, and mostly in the United States they use tempered glass. Of course, you can overcome the problem of safety with lamination, yeah? But what about the thermal stress, yeah? Which is probably also here important due to the fact that you used some coatings. It was hard coatings, if I got it right, or?
Correct. That's a very good question and very important. That was some of the. I'm going to go back to the collaboration efforts that we did, and one of the things that we needed to make sure is that whatever coatings we found could meet the thermal performance, but also make sure that the glass would not break because of thermal breakage, basically. So the coatings that we had to find were very clear coatings, and one of those was the XIR interlayer, which has a coating on the interlayer. It's a coating similar to, I don't know if you're familiar with the coatings, triple silver, basically. A coating like a Sullivan 70 in the US or SNX 6227. And then the low E that we used was a very clear coating. It's an energy advantage. It's a North American product. It looked almost like clear glass. So the absorption of the glass is, the thermal absorption of the glass, it's low. And so we minimize the risk of thermal breakage by doing that and still met the thermal performance that they needed in the building. There's a question over here.
Also in terms of U value, because if it's laminated,
yeah.
I don't know how cold it gets in Detroit in the winter.
Correct.
Maybe they don't care about climate change and stuff like this.
The structural performance was very important, and so the IGs did not work given the installation method that they were going to use. Also, the way that we placed the coating was on the number 4 surface. So while we did not have the U values that you would have achieved with an IG, the U values were reduced compared to a regular laminated piece of glass because the low E was on the number 4 surface, which was in contact with the air. So that was a way to accomplish a better U value, even though it wasn't an IG unit. Yeah. And I forgot to mention also the edges of the glass were polished, so for thermal performance.
So do we have any more questions from the audience? Okay, because we have about a minute left, I'm going to raise the last question. What about the rejection rate? Because you've shown that the architects came to your premises and inspected the glass. So what are the kind of typical rejection rates during your processing, during your in-house quality control, and then when the architect comes to check the glass?
Well, when the architects came to check the glass, the rejection rate was very low. I want to say maybe we rejected 3 pieces out of the whole project after they were finished. Internally speaking, the reaction rate is higher because we go through different quality checks, and we do have rejections internally. I could not tell you a percentage, but it's under 10%, but it's still higher than final product rejections. Yeah, yeah. So that's one of the things that we gotta make sure that in curving glass there's breakage and there's things that we gotta replace because it's not meeting what the quality that we need.
Okay, so thank you.
Good job.
Hi there. Did you like what you just saw? If you did, why not like the video? Drop us a comment below, as well as share the video with others, since GPD is all about sharing. And to receive more videos in future, subscribe and don't forget to click the bell icon for notifications. Ciao.